All right, welcome to another edition of Battery Corner, aka everything you wanted to know about EV batteries but were afraid to ask. My name's Ryan Austin, CEO of Lyteflo. We have Battery Alex here, our director of battery intelligence at Lyteflo. Battery Alex, how you doing?
Doing well. Can't complain.
Good. Fast moving week in batteries as always. Super exciting. Okay, so let's jump into it. On this show, we answer top of mind questions about EV batteries and EVs in general. So I want to start off today talking about the 12-volt battery. So many drivers are surprised to learn that EVs have another battery, a smaller battery, a 12-volt battery that's like the battery in a gas vehicle, and that thing can also die and is quite susceptible perhaps to dying, certainly more than the high voltage battery. So Battery Alex, tell us about what the 12-volt battery does and what problems it may encounter.
Yeah, so literally, like people are often surprised to learn that your like fancy new EV with this massive lithium battery and it still has an old lead acid battery inside, exactly like an ICE vehicle. And most of that just comes from the fact like a lot of it's legacy and then a little bit of safety is involved as well. So basically like the big battery in the EV operates at high voltages. Like it can be north of 800 volts these days. So it can be a little dangerous to leave it connected to all the power electronics in the car all the time. So there's these big contactors that are these physical switches that connect and disconnect the big battery from the car, but those need to be powered by something. So we have a 12-volt battery in the car that can handle all of these little auxiliary functions and like wake the car up basically when it's off. So that's why it's still hung around. And then also a lot of systems in the car are designed to work with these 12-volt batteries. Now you can step down the voltage of these high voltage batteries to be 12 volts, and in operation that's normally what happens, but you still need to wake up the car and things like that. Or if there's like a crash and the car needs to power off, but like a lot of cars have powered doors and stuff, like those still need to be powered, and the 12-volt battery can handle that.
Why not wake up the car with the high voltage battery?
It's just because we don't only leave the high voltage battery in contact with the whole system, because like you need a lot of safety electronics on the battery. It can like self-discharge a little bit. Like it's mostly just for safety that they do it. But
why is it not safe?
It's because then you have like an 800 volt battery connected that has to have like the proper isolation, and it has to have the proper like regulation on the battery itself, so that you don't like.
Doesn't it already have all of that?
It does
safety?
have it, but it consumes power to do it though. So it's like it's more efficient to just disconnect everything and leave a small battery to handle like the small operating features. There's probably some other reasons. Now, like as a battery chemist, I'm not a vehicle engineer, so I'm just going off of what I've read and learned from the industry over the years. But yeah, like the other thing is too, just like a lot of these like parts that manufacturers use are off the shelf and are designed to work with this voltage. But yeah, it's just, and you have losses when you convert down to 12 volts too. So if you have like, it's kind of overkill to switch on your massive battery just to convert it down to 12 volts idle, waiting for you to press the on button, when you could just take your lead acid battery and let it sit there.
Got it. So what are some of the ways that this battery can die in an EV?
So yeah, so basically it's just, if your EV's not on and something's consuming power. So the EV is always consuming a little bit of power, like waiting for your key or like to respond to like your app or like with little internet connection things and stuff. Like
you think it's off, but it's not.
Yeah, your EV is never like fully off, because it needs to make sure it's like, it needs to check in on itself basically. And it has connectivity with the manufacturer and all this other stuff. So that consumes the battery when idle, but normally this is a small power draw, so it's okay and it's like intermittent, so it's okay to leave it for a long time. The other thing is like if you have the car not fully contacted, like this depends on the car, like the manufacturer and the model, but you can have like the different levels of on within your car. And some of them still just rely on the 12-volt battery. It's the same thing in your gas car when you don't start the engine and you have like your radio on or like the light on or whatever. You can do that in some EVs where the full battery isn't being engaged because it's a small power draw operation. So it's just like, oh, okay, like you have a little internal light on or something. So you can drain your battery kind of in the same way that you can drain it in an ICE vehicle. In some models anyway. Some of them like are a bit smarter about it, but yeah.
Okay.
Yeah.
So these vehicles have come a long way, but we're still relying on some of the old technology.
And just over time, lead acid batteries fail, as anyone with an ICE vehicle knows. So then all of a sudden you could get in your EV that's fully charged and you can't turn it on because the lead acid battery. This happened to my dad like a few months ago, actually. Yeah.
Okay, great. Let's move on to solid state batteries. So solid state batteries are every month it seems we'll have some news about some company, perhaps named after a food or something like that, that has had some breakthrough in solid state batteries. And I know the OEMs have been working on solid state batteries for a while, and that the large battery manufacturers of the promise of faster charging, longer range, all of these sorts of things. Tell me about what solid state means and what is the impact of having solid state.
Yeah, so now they're finally actually becoming production vehicles with solid state batteries. Like Donut Labs is obviously who we're referring to.
Is Donut Labs real?
Donut Labs.
Is their technology, is the promise of their technology real?
So the promise of solid state is real. It's just a matter of who's executing what. Like everything is still not independently verified. So that's like the main hurdle right now. So let's just talk about what solid state is and like why we care about it. So with the traditional lithium battery, it's an anode and a cathode soaked in this electrolyte. And that's so it's like we got two plates. Your lithium can shuttle between them, but to move between them, it can't go through air. Like it needs to kind of like go through something, and that's the electrolyte. So it's all soaked in this liquid. And this liquid's highly flammable, so that's what causes all these fires. Like if the battery shorts, it heats up, ignites this liquid electrolyte, and then that's the fire. So the problem is we don't want our batteries to catch on fire fundamentally. And then the other problem is the current materials used in these batteries are not the most theoretically efficient materials. So basically, we've talked about the cathode a lot because that's the NMC, LFP, like you hear these like thrown around in the news and everything. But on the other side, the anode, which gets a little less attention, that is traditionally just carbon. So it's like graphite. It's like pencil lead, basically. And then nowadays they mix some silicon in there to make it store a little bit more lithium per mass and per volume. But the problem is, in an ideal world, you would just have pure lithium because there's no real chemical reason why you can't just have lithium sitting on the other side, just pure. Like there's no carbon it has to
on
go
the
into.
anode?
Yeah, on the anode, exactly. Because if you just have lithium, then you only take up the space of the lithium ion atom. Like
you can have more lithium.
Exactly.
More energy
it's way
density.
more dense. Because instead of having 6 carbon atoms for every lithium, you have nothing. It's just lithium. But the problem with that is if you try to do that, you get what's called lithium plating and dendrite growth. So what happens is lithium doesn't just make a smooth sheet when it settles over. What happens is it grows spikes, and those spikes can puncture the separator that keeps the cathode and the anode separate. That causes a short, that causes a fire. So that's why we can't do it. The promise of solid state is to basically enable that savings, because a solid barrier, like if your electrolyte is solid, so all a solid state battery is we take that liquid electrolyte that allows the lithium to flow and replace it with a solid material. Now this could be a polymer, it could be a ceramic material, and
so it's literally like clay, or what does that mean?
So basically it can be like a gel like material, or it could literally be like a firm like ceramic, like clay, like kind of like clay texture and feel wise. But and it's a little unintuitive to think, how can like lithium transport through that, right? It's like,
Yep.
because through a liquid it makes sense, like things
Yeah,
can like move around.
my brain is confused about how the lithium would go through that. That was the first thought I had.
Yeah, so it's a little bit strange because the problem is you can't really, like, we think about this transport kind of macroscopically. Like if you put little bits of like, I don't know, like sand in water, you can see how they flow around in the water or whatever. But if you have a solid, like what happens? But one way to think about it kind of more analogously is to think like how you can have electricity flow through copper. You know, like you have electrons move through copper. Now, it's not at all the same mechanism, but you can think of it kind of in that way. It's like something can flow through a solid at like the tiny, tiny like atom level. So basically, lithium can kind of temporarily sit inside this material. So this material contains lithium, and think of it more as a little bit of lithium kind of like pushes another lithium, which pushes another lithium. It's like a chain reaction rather than a single lithium ion swimming through the whole material. So it's kind of like you have this situation instead. And what the advantage of that is, if you have a solid, physically stable, strong thing, lithium can't grow a spike through it, just like it can for a liquid. So the idea there is you save a lot on volume and mass because you no longer need an anode material. You just use lithium, and the lithium directly plates onto your current collector, which is just a metal like copper. So that's the main advantage. And then it's not flammable because you don't have this flammable liquid electrolyte. So it's kind of like a twofold advantage. You get no like it's not flammable, and you get better energy density. Now, the main problem with all of this is the reason why we use a liquid is because it makes all of the materials accessible to the lithium because it soaks the whole thing. The problem with a solid is you have a big interface. So you're trying to press it up against each other like this, but then as the lithium comes and goes, it expands and contracts, and then you get breaks between the two surfaces. And lithium can't go over like an air gap, basically. So that's the main problem. So it's this interface engineering that really holds back solid state. And that's what people are starting to overcome now to deliver it into EVs.
So you have to prevent these cracks or figure out how to deal with these cracks.
Exactly.
What about degradation? Is degradation profile change at all?
Yeah, so that's basically what everyone's trying to solve right now, because historically they degrade very quickly because any of this interfacial cracking or like this loss of contact means that's kind of dead material now. Because wherever the loss of interface is, you get either high resistance or just resistance so high the lithium can't even go in anymore. So it really remains to be seen, because like in liquid batteries, it depends on the materials used and the processes used. So like there's different ways so a lot of batteries are using like a hybrid approach where you have kind of a gel, but the gel is soaked still in a liquid. So you can kind of get the best of both worlds a little bit, where it can suppress the dendrite formation so you don't have those spikes, but you still have kind of the high availability of the liquid to conduct. Exactly.
Almost fill in the cracks.
Exactly.
Kind of thing.
Exactly.
And so is this a game changer that everyone says it is? Is it a game changer? I understand the flammability and, but we do know that the risk of fires is fairly low in EVs. Is it a game changer? And is that, and why? Is it because of energy density, cost?
Yeah, so it becomes a game, it remains to be seen, basically, because it's going to come down to manufacturing cost. So as soon as, if the companies that are promising solid state, like CATL, if they can deliver on the range, if they can deliver on the proposed energy density that they have and the lifetime that they say that they've achieved, then it starts to become a game changer, mostly because of the energy density. And because if you make it not flammable, you don't need as heavy protection of the battery. So that's a whole, there's a whole engineering thing. So the cost comes down, the weight comes down. Basically it's like a win-win-win, but it's all held back by this interfacial engineering. So that's the challenge. So if these companies are solving it as they're claiming they're solving it, it will slow it, but it's not going to be like an overnight game changer. It's basically we're making these incremental improvements. We kind of, once it gets good enough to use, it gets adopted, but it's still not as, in its optimal form, it's a game changer, but we have not reached its optimal form, basically.
Great. All right. Well, there you have it. Looks like it is a game changer, but we're not yet there.
Yeah, the game hasn't been changed.
The game hasn't yet been changed. At some point in the future, it may change.
The game is subject to change. But,
yeah, it's a race. It's a race for solid state batteries.
Yeah, exactly.
Yeah. All right. Well, that concludes. I think we'll leave it there, concluding another episode of Battery Corner. Battery Locks, we will let you go back to the lab. We let you out of the lab for Battery Corner. He's going to go back in the lab now. And we'll see you next time.
All right.
Thanks.
Sounds good.
Bye.